years. This is the second time. How you call it? This is the second time he has been able to come on my platform. He's going to be talking to us about our topic again is broadcast flow. I think it's broadcast. It's point source and line source. And without wasting much time, I would like to hand over to Mr. John Oben. Hi, John. Can you hear me?
Hello everyone. Hello, Steve. Great to be back here. Yes. Can you see me? No.
No, I cannot see you yet. Let me see. I cannot see you yet. Let me check. Let me check the teams. You have to share your... Okay, let me share. It's already shared, but we can't see you yet. We can only hear you. Can you open your video?
Yeah, let's try and get that done. Just give me a second.
Okay, while we are at it, guys, Mr. John is the Pro Tech head for product technologies at YAMAHA Corporation, Dubai. And he's going to be teaching us both theory and practicals on some fantastic aspects of speaker and how we can manage it optimally. So they're trying to connect with us.
Okay, wait. Yeah, just give us a quick minute to get the video going.
Okay.
Okay, in the meantime, while we're trying to do that, yes, Steve, thank you again for having me on. I loved your flow. You know, you really good at it, and a great experience you're sharing with the people online. Yes, as Steve said, I just said
Okay, try it again, please, John.
Check 1, 2. Check. Can you hear me?
Okay. Please, can you guys hear him?
Check 1, 2. At any point in time you lose me, just find a way to.
Yeah. So yeah, someone sent me a message. Let me confirm from them. So, John, please keep going on. Just keep talking. I'll see how we can rectify this.
Okay. All right. Do I have now? Everyone hearing me? Everyone hearing me?
Once it's back, just give me a message. Okay, try it again, John.
Check 1, 2. Check. Check 1, 2. Check 1, 2. Sound check. Live sound check. Broadcast sound check. 1, 2. Check. 1, 2. Check. Can you hear me?
So I can. I think I'm capturing.
Can you hear me? Check 1, 2. Check. Check 1, 2. Check 1, 2. Check 1, 2. Check. We have sound.
Let me check something here. I think.
Check 1, 2. Sound check.
Okay, let me check the audio from. Let me check the audio from. Try it again, John.
All right. Can you hear me?
Okay, John, can you please check your audio transmission? John, can you please check your audio transmission from there?
Transmission is fine, and we're also transmitting on another computer, and that computer is really.
Okay, so it should be from our end here. Let me quickly check. Go on, John. Please try again, John. Hello, John. Can you try again?
Yeah, I can hear you. I'm speaking continuously.
Okay.
Check 1, 2. Check 1, 2. Now, let me see and of here. Check 1, 2. Check 1, 2.
Okay, hold on a second. Let me check the audio. Let me check the audio to Let me try that and see. Okay, so can you try it again? Let's see. Hello, John. Hello? Hello?
Yes, I can hear you.
Okay. Yeah, I'm trying to check the website and see, or rather the YouTube page and see. Okay, so I think what's happening is they are hearing me, they are not hearing you. So let me, um, yeah, let me change. Let's see. Okay, so can you try it again? Let's see. Okay, John, can you try it again? Let's see. So, John, can you help me speak a little bit? Hello, John. Can you help me try that again? Hello, John. Okay. Hello. Okay, John. Can you send me a link? So I will open the link and share straight on OBS. So you are the host because yeah, I'm having difficulty here with trying our platforms here. So guys online, sorry for that. Guys online, we're trying to rectify it. So just send me the link for Teams, and we will just yeah, we will just quickly.
I will go up, I will then send you the link.
Yeah. Okay. Thank you. So hi folks. Hi folks. Apologies for that. Apologies for that, but we needed him to send us a link instead, so that we will get all the feeds directly from him. So that's what we want to achieve right now. So in the next 2 or 3 minutes, we should be back up with you guys. Just bear with us. I'm just waiting for the link from YAMAHA office, and then we will take it up from there. So kindly bear with us. Apologies. Hi, John. Hello? Hello, John. Can you hear me? Hello, John. Hello, John. Can you hear me? Hello, John. Can you hear me? Hello? Hello? Okay. Hello, John. Can you hear me? Interesting, because we tested this earlier today and it works. John, I'm on hold. I don't know why I'm on hold. Okay, okay. Hi, John. Can you hear me? Sorry?
Hello, Steve.
I can hear you very well. Go, go on again. Please try it again.
One, two, check, sound, check, check, one, two. Are we making all the way to YouTube? One, two. Check, one, two. Check, one, two. Check, one, two. Check, one, two. I can't hear you though. If you're, but I see you speaking.
Can you bring your picture out?
Check, one, two. Check, one, two. Check, one, two. Check, one, two. Check, one, two.
I can hear you, John.
Can you?
I can hear you.
Yes.
But I need you
Can you
to
see me though?
open your camera. No.
Okay. You will see me in a second. One, two, sound check. Camera check. One, two. One, two.
Fantastic.
Check.
Yeah, I can see you now. Fantastic.
Awesome. Awesome. Okay. Are we all hearing me? One, two, sound check. Sound check. One, two. One, two. Hello, hello, hello. Sound check, sound check.
John, can you do a full screen? A full screen.
How do you mean full screen? Full screen. Okay, 1 second. Okay, I think it's on full screen right now. You should be able to see me entirely. Okay. Yes. Full screen. Yeah. Check, one, two. Sound check.
John, we can hear you. We can hear you now. Please proceed.
Say again. Steve?
We can hear you online. Please proceed.
Oh, you can hear me. Oh, fantastic. Okay. Fabulous. All right. Thank you very much. Okay. So where was we? Gentlemen and ladies, sorry for all the technical glitch. I'll just try to make sure that I go through this really quickly, so we can get as much as we can. All right. I did ask a question before, and the question was, what's your definition of point source? And I hope some of us have been able to put out something to Steve, so we can preview before I continue. Do we have something, Steve? Anyone?
We don't have anything yet.
Okay.
But I will share the
Okay,
YouTube page with you as well, with your guys, so they can just look at it.
Okay, fantastic. All right. So, like I said, the purpose of a loudspeaker system is to provide all of the audio geometry with an even coverage of sound. And the most coherent way of achieving this is to use as few sound sources as possible. And loudspeaker systems fall into two classes. I'm just trying to go over what I already said to create some kind of continuity. So we have point source, we have line source, we have column speakers as well, but broadly speaking, point source and line source. Each system has its own benefits and advantages over the other, but both are still in use and viable into this PA industry. And I'm sure your experience bears this out. Okay, moving on. 1 second, just give me a second. Okay, so what is a point source? Okay, yeah. So what's the point source? A point source, so if the source of sound is much smaller than the wavelength of sound it emits, it can be represented by a point source or monopole, and it will tend to radiate sound equally in all directions with spherical symmetry. Now, all that jargon, I'll try and distill it into a much more simpler, explanation. So basically, a point source typically would be, or you can describe a sound source as a point source if the criteria is there, if the wavelength being emitted by that sound source, with the frequency being emitted, the wavelength of that frequency is larger significantly than the source itself. It means that it will tend to radiate the sound equally in all directions with spherical symmetry. Now, I'm very, very particular about the terms I'm using. You will see why in a second. Now, some of us will probably know the definition, some of the characteristics of sound. Sound reflects, right? And sound diffracts, meaning that sound can bend around objects. So if the sound has been emitted, the wavelength is larger than the enclosure itself, that sound is going to bend around it. It's going to diffract pretty much. And when it behaves like that, it is behaving like a point source. And radiate equally in all directions with spherical symmetry. So there will be symmetry. It's going to radiate all around and equally. Now, take for example, a hypothetical cube, a cube-shaped sound source with, say, 0.3 meters in dimension, emitting an 85 hertz sine wave. Now, what is the wavelength of 85 hertz? We know that the formula to calculate the wavelength is the speed of sound divided by frequency. If you do the math, that wavelength is going to be like 4.03 meters, right? Now, remember the size of the enclosure itself is 0.3 meters. The wavelength of the 85 hertz is 4.3 meters, which is basically like 10 times the size of the enclosure. That enclosure is going to behave like a point source. It meets the criteria of radiating sound in all directions, equally and symmetrically. Now, this is very, very important, as you're going to see as we go down the line as we go even deeper in what point source is and how it behaves. So I'm going to play this animation. You can see sound emanating from a point, and it is radiating spherically in all directions and symmetrically. So any system that meets this criteria is a point source. Any system that fulfills this criteria is a point source. Okay? All right. So a point source system is one that originates from one point physically or virtually. So a single speaker can be considered as a point source, as can an array of multiple speakers. As you can see in the array of the single point source and then an array, as displayed in the illustrated photo. Now, point source speakers, like I mentioned before, there's column speakers, and then we have line arrays. Now they have their advantages, and then they have their disadvantages. And I'm just going to look at them point by point, and then see how we're going to build upon that, going forward. Now, let's start with the advantages of point source speakers. So point source speakers are versatile. So basically versatility of style and deployment options. So this ties in with your experience, I believe, where you have an 8-inch point source, maybe 10-inch, you have 12-inch, 15-inch or more, So you have different sizes that can fit into different application environments. And then you have also versatility of deployment. So you can deploy them sometimes, you can fly them, you can wall mount them, you can put them on the balconies, or you can also deploy them vertically or horizontally, depending on what you're trying to do. So you can see point sources are very, very versatile. Now, you also have point sources. Another advantage that they have multiple coverage options, because there are some point source brands that have, 60 by 60, 120 by 40, 120 by 60, 90 by 60, 100 by 100. So you can see point sources have, so you can see multiple coverage options that you will not find in any other, system. So that's an advantage that can be useful for certain applications that you want to do. Also, you have consistent horizontal coverage. So you have your horizontal, you have maybe 60 by 90, and the different, coverage options. Consistency. A good thing about point source, of course, is that system price is affordable, and it's within reach, many users to acquire. Now, you can think of any other advantage, from your experience, but I mean, to mention a few, that kind of covers, some of the main. Now, moving to disadvantages, you have what we call the low frequency limitations due to pattern control. Now, what I just expressed right now has a little bit of math to it, but I'll pack it now and I'll cover it a little bit later. Okay, but pattern control is a limitation that point sources are not able to achieve. Okay, arraying challenges. You cannot stack many point sources to improve, maybe their coverage or the SPL or any other thing like that. So there are challenges, involved in, doing that. And I'll come to that a little bit later, but it's important to actually have that in mind. Now, also, point sources have limited throw distances. And then, of course, combined clusters act as multiple point sources. And also you have the high drop off with distance. So you have, when you double your distance from point source, you're going to have the SPL pretty much. So they're good for mid to near field than you will want to deploy a point source for when you want to do long distances. Okay, so keeping that in mind, point sources doesn't mean they don't sound good. They sound great, but if they're used for the right application environment, point sources can sound fantastic. They have this open sound, and they can be very, very, powerful. All right, so I'll move on to column speakers. One of the reasons why column speakers, can be, is the aesthetics. They look slim, lepa, very nice looking, and they fit into the aesthetics of the venue or where they're going to be deployed. So they look very good. They're cost-effective way to provide the vertical pattern control that you do not have with point source. Okay, vertical pattern control. And there's also consistent front to rear and low frequency coverage like full-sized arrays. The great thing about line arrays is the front to rear consistent coverage. That also you can get from a column array. Affordability with reduced rigid requirements and amplification. So you have, it's affordable. It behaves like a line source, and pretty much within price range a lot of people can afford. And then they are efficient in highly reverberant environment. Basically, they take on the characteristic of a line source, like a searchlight, a touchlight, or sorry, a flashlight that can just point the sound source to where you need it to go without hitting ceilings or walls. So it's focused. Disadvantages for column speakers will be SPL consideration because they don't have drivers as large, like a typical, line array. So of course, SPL, will be moderate. And then rigging situations like in the height, because they are long, so you need spaces with good ceiling height for you to properly deploy a column speaker. Okay, I'm sure you can think of some other disadvantages. Okay, so for line arrays, we know the typical advantage or selling point of a line array is the fact that, with a drop off of distance, you lose just 3 dB when you double, your distance from the source. So that makes it very suitable for long throw because you're losing less of SPL as you go away from the source. And so there's precise vertical pattern control because of the line length of the line array. Stack 4 meters, 5 meters, so you can see how the line length will allow you to control, the frequencies down to quite low, down to 85 hertz even. You can have some serious pattern control there. Of course, line arrays with the contribution of every cabinet, it makes for summing, and that summing helps with the high SPL capability of a line array. And of course, because it's very efficient in very highly reverberant environments. All right, so for disadvantages, you have less efficient, for line arrays are less efficient in shallow rooms. Of course, you need shallow rooms, line array, not a good idea. It requires the rigging height, also requires suspension points. Because of safety, you need reinforced ceilings and all of that. So all the safety factors structural engineers. So a lot of discussion needs to go on and a lot of consideration before you want to deploy. Okay. And then, of course, less effective when they are ground stacked. If you want to ground stack a line array, there are procedures and ways to to get it done, and I'm sure we'll probably get to that at some point. And then system price is always quite exorbitant, so sometimes out of the reach of a lot of end users. Of course, for some people, money is not an object, so maybe that may not be a disadvantage. But at the end of the day, for majority of people, sometimes it's a bit prohibitive. But the advantages sometimes, for long distance throw, for long throw, for big audiences, line array is what you want to use. Okay, if there's any question from what I've just said so far, maybe you can just also put it across to Steve and let me know, and then I can try to address it. And I hope that we're all hearing me loud and clear this time around. Steve, can we check? Am I coming through?
Yeah, you are, John. You are. Can you hear me too?
Okay.
Yeah, so
I hear you loud and clear.
Dr. Dre just explained, he said point source is a kind of speaker system used in a medium and a low headroom event hall. That was the statement he dropped. So, guys, if you have any questions on the statement, you just drop it in the chat room and we'll read it out. Thank you.
Fantastic from Dr. Dre. I mean, you just kind of echoed some of the things I just explained. So thank you for the contribution. You're 100% correct. All right. So going further into point source. So what is the ideal point source? And there's 3 sticking points that I'm going to try to direct our focus to. One is surface in 3 SPL. Surface area speaks to coverage. Intensity speaks to energy. And SPL speaks to sound pressure level, which is how loud we can perceive the system. Which are 3 key things you want to have or you want to see and how the system performs. So what we're trying to look at is how the energy changes across the surface area each time we double our distance from the source. Keep that in mind, how energy changes across the surface area each time we double our distance from the source. And then also want to look at how much energy is on that surface area of the sphere that is created. And that's the intensity. And finally, how does the sound change as we double our distance from the point source in terms of SPL? Okay? How it changes. So keep that in mind. So you can see we from the animation I played before, you can see that point source radiates spherically, right? We said it radiates what? Spherically, it radiates equally in all directions and symmetrically. Yeah? Okay, so you can see from the illustration there, let me see if I can. So you can see here, this is the point source. That's the point. And this is the first ripple. And then you have another ripple. There could be more and more, And then you can see the surface area A from the point. And then double the distance 2r. We have 4 squares. That is 4 quadrupled surface area of 9 times over the initial, surface area. Okay. Now, first thing we have to consider is we're talking about sphere, right? Now, what is the area? Surface area, which speaks to coverage. Coverage is about area, right? So, and a sphere is radiating. So, we want to know what the area of that sphere is covering, being a point source. All right. So, the sphere, this area of a sphere is 4 pi r squared, where r, as we've already indicated here, r is the distance from the point source measured in meters. Now, we said how much let me go back. How energy changes, the first bullet point, how energy changes. Okay, in this equation, squared, what is changing? The only thing that's changing is r squared, because we're changing from r, but the only thing that changes is r. So we're changing from r to 2r to 3r and so on and so forth. Everything else is constant. So we do not need the constant. We're interested in how it changes as we double our distance away from the constant. Since we're only interested in how the sound is changing, we arrive, so you eliminate 4, eliminate pi, which is a constant. So we have area is equal to r squared. If you do the math, it means that if you double your distance, you quadruple your surface area. When you double your distance from a point source, you quadruple your surface area. Now, what does that mean in terms of application? It means that a point source is great at disseminating sound over more area. It's great at coverage, great at reaching. So when you double your distance, you quadruple the surface area. You double, you quadruple. So if you have a theme park, for example, where you want people to hear sound across different areas, the best solution there will be what? A point source, because you want it to spread as far as is possible. Now, if you have a reflected space where there's a lot of reflection, what you don't want is a point source, because it's going to be reflecting. I mean, it's going to be, surface area is going to increase by a factor of 4, exciting the reflective surfaces and create a lot of reflection. Yeah. So you can see now where a point source can be effective and where it cannot be effective, just because of the physics of the propagation of the sphere of a point source and how it affects surface area. Do you understand? Any question, please feel free to and I can really back up and try to come back again.
Okay.
All right.
John.
So, yes.
There's no question yet, but once they drop it in, I will just, highlight, notify you, and then read out the question, if that's okay.
Okay. Yes, that's fine. That's fine.
Okay.
Okay. Thank you very much. So I'll go on to the next point. And what's the next point? So intensity. Intensity. Now, intensity, if I go back a little bit, I said how much energy is on the surface of the sphere that is created. So remember, the point source, we doubled our distance from it and we had 4 times the coverage area, correct? Now, 4 times, what is the energy we have in that surface now? That we have 4 times the coverage area. So, of course, intensity, from your physics in high school, intensity is given by power over area and is measured in watts per square meter. How many of us remember that in physics class? All right. Now, P is the power of the sound source measured in watts. And so P is power. A is what? 4 pi r squared, like we encountered when we looked at surface area, right? Okay. So, and we say that what is changing? The only thing that is changing there is R. P is the same, because same power that was resisting when you were at R, the same power when you're at 2R or R squared, and so on and so forth. So power is constant. 4 is constant, pi is constant. Only interested in the variable factor. If you work that out, eliminate all the constants, you have intensity is inversely proportional to the square of the distance, which means that when you double your distance from the point source, you're going to have 1/4 the intensity. So the sound gets weaker the further you get from a point source. And that tells you one thing. When you say point source is good for medium, not long throw, that is the reason, one of the reasons why. Because the further you go from the point source, the weaker it gets, but the more coverage you get at the same time. I hope we understand. So that's one of the reasons why point source is always medium to short throw, and not for long distances. You understand? It's just like, say you have bread. You take your bread and you slice it into four. Take butter, a certain quantity of butter, and put it on one of the slices that you've already divided. Use the same quantity. You can see the thickness of the butter in that one of the divided slices. Take the same quantity of butter and spread over a full slice of bread. You're going to have more butter over the bread, but less concentration of butter over the bread. Much that illustrates what intensity is, for sound. So remember, for surface area, you double the distance, you quadruple the surface area. For intensity, you double the distance, and you have a quarter of the intensity. Okay. Finally, so you have the when we talk about the SPL, which interests a lot of us, and that would take us a little bit to the fundamentals of sound. Sound there's particle velocity involved in the transmission of sound. You understand? Because sound is like a spring. As I'm speaking in an acoustic environment, you have particles that are vibrating, bumping into each other. So one particle hits the next particle, transfers the energy to the next particle, and they keep vibrating back and forth, and they keep hitting. So you have compression, you have rarefaction. Like a spring compresses and expands. And the sound energy transfers from one point as it gets to your ears. So what is really happening is sound particles that are bumping into each other and transmitting the energy from point to point. The speed of sound at 343 meters per second, really fast. Okay. So if we go down into our first here, okay, that this is the first area, doubled the distance. This is the second area, triple the distance here. If we quadruple it, you're going to have something like this. So the first distance, that is R, okay, with intensity I. So let's say it has 16 molecules of particles of sound. Let's say it could be anything. Excuse me. So we have one R there. We doubled our distance. We have 4. And remember, when we double our distance, what happens to the surface area? It quadruples. So that's what happens here. So we have, now, why do we have 4 particles in each of the squares? Remember, what strictly. Because of that behavior, we can expect to have 4 particles in each of the surface areas. Now, if you triple the distance away or you quadruple, you're going to have 1, 2, 15 surface area with 1 more surface area. Makes sense, because we double our distance, we're going to have more coverage, 4 times the coverage, and we have a fourth of what? The intensity, right? When we have 4 times the surface area, we're going to have another fourth of it. So you can do the equation down the line like that. So our illustration here kind of fits the profile: 1R, 2R, 4R. So we have the different intensities, the different surface areas expressed here. All right, that's it. We're talking about SPL, right? So sound pressure level. So what is pressure? I mean, we're talking about pressure, basically. So pressure which we've already covered before. Z is the acoustic impedance. We're talking about as sound transmits from one medium to another. In this particular situation, the sound is not transmitting, it's transmitting basically from what? From air to air.
Hello, John.
So acoustic impedance,
Hello?
yes.
Hello, John.
Yes, I can hear you.
Yes, sorry, can you take that line again? Can you take that part again where you talk about sound pressure? Can you go back like 2 steps a bit? Because we lost your audio. I think it's from the network.
All right, I'll back up a little bit. All right, so basically, I was coming from the point where you have the ideal point source from a sound pressure level point of view. Now, from the diagram you have R with A, 2R, you have 4 A's, 3 R's, you have 9 A's, and if there's 4R, you're going to have 16 A's, 16 surfaces. So, and we started off with hypothetical 16 particles of energy expressed in the intensity. And we have 2R. When we double our distance, which is 2R, the surface area, we quadruple the surface area, which is why you have 4 squares, 4 areas under 2R, right? If we quadruple again from 2R to 4R, we're going to have 4 times that amount. You're going to have 4 times the coverage area and a fourth of the intensity by a factor of 4. So we have in 1R we have 16 particles of energy. In 2R we have 4 per square. In 4R we have 1 per square. The reason why we have those particles is because sound, when it radiates, when point sources radiate, they radiate what? In all directions. They also radiate where? It's symmetrical. You double your distance, you're going to be increasing your what? Your surface area, and then you're going to be reducing your intensity by a factor of 4. All right. Now that said, we're looking at pressure, SPL. And pressure is given by intensity times acoustic impedance in square root. The intensity times acoustic impedance square root. Now, what we're looking at, what is changing? What is changing here is the intensity is changing. In terms of it is dropping by a factor of 4. It is dropping and it keeps on dropping that way. Acoustic impedance, which is Z, is not changing. Why is it not changing? Because acoustic impedance has to do with how sound transfers or transmits from one medium to another medium. In this particular situation, sound is not changing medium of transfer, it's within air. Okay, so Z becomes a constant. So if we do the math, P, which is pressure, is basically the square root of intensity. How do we get? We've eliminated the constant. The constant is acoustic impedance. Done. Now, if you convert, so P basically becomes the square root of intensity. Now, if you convert 16 bits of energy into pressure, you'll have P is equals to the square root of 16, which is basically 4 Pascal. And that's our reference. Now, if you double your distance, which is 2R, so P is equals to what? The square root of impedance, which we have 4 bits of energy. Convert that to pressure. P2, which is our measured distance, which is 2R, becomes the square root of 4, which is 2 Pascal. Going further, remember the log equation for SPL. Basically, measured over reference. What's the log measured over reference? What's our measure? Is our expected distance change, which is 2R. So our reference is P1, which is what we started with in the first place, which is R, 1R. So where P1 is 4 Pascal and P2 is 2 Pascal. So if we use the formula 20 log measured over reference, we get 20 log 2 over 4, which is 20 log 0.5, which is minus 6 dB. So it means that when you double the distance from the point source, you're going to have a 6 dB drop in SPL. So every time you hear, when you change distance, you double your distance from point source, and you have 6 dB SPL. That is the equation where it came from. Okay? Do we understand? Any questions?
Yeah,
Yes.
I have a question. So
Yes, please.
does this really matter the number of speakers point source? So let's assume we have 12 speakers in a stack. All right. Will this still based on the distance now, the change in the distance due to the how you call it, the calculation, the SPL calculation, will we still have to lose that 6 dB of SPL?
Okay. When you say 12 on a stack, you're talking about 12 point sources stacked together, right?
Yes, I said let's assume.
I lost you there.
Can you hear me now?
Now I
Hello?
can.
Hello?
Now I can hear you.
Okay, I said let's assume.
I can hear you now.
Okay, let's assume we have 12 boxes in one, stacked together, point source speakers. All right. Does this principle or rule still apply that we'll still lose minus 6 dB of SPL irrespective of the number of buses in the stack?
Can you hear me?
Yeah, I can hear you.
Can you hear me?
Yeah, can you hear me?
Okay,
sir?
give me a second. Give me a second. Yeah,
Okay.
I can hear you. Give me a second, please. Yeah.
Okay.
Okay, can you hear me now? Hello? Hello? Can you hear me?
Yes, I can.
Okay, yes. Of course, any point source situation that you find, always you're going to lose 6 dB. If you like stack a million together, as long as you describe it as a point source, you always lose 6 dB. Now, of course, there's other issues that have to do when it comes to stacking point sources together. Yeah, and I will address that in my next. I'm going to try and cover that within 20-30 minutes. Okay, and I will address that point. Hello? Can you hear me?
Yeah, I got you.
Okay, fantastic.
Thank you.
Okay, yeah. We've spoken about point source.
Sorry,
Yeah.
sorry,
Now,
sorry.
yes.
So it's not as a consequence of volume of speakers, but it's as a consequence of the ratio of the principle that governs the pressure level. It has nothing
Correct.
to do with. Okay. All right.
Absolutely. In fact, you captured it nicely. Yes. Okay. Because once the sound leaves the cabinet and it leaves in a spherical manner, it is a point source and it will obey those laws.
Okay, sir. All right.
Okay. So that said, of course, if there are any other questions, you can put it in the chat, and I promise you I will address every one of them and get back to you. All right. So moving forward, so basic line source theory. So it's going to get a little bit interesting here. So I'm going to talk about line source. Point source, line source, I already covered that before, so I don't need to really spend time there. Then we'll look at line source vision. Okay. All right. So what is a line source? A line source is a series of speakers covering the same frequency range, placed in a line, typically vertical, and the speakers are at slightly different vertical angles, which allows them to cover a greater area than one speaker by itself. Series of speakers, they cover the same frequency range, placed in a line, typically vertical, and placed at slightly different vertical angles, which is display angles, and allows them to cover a greater area. And now, any other definition, I'll be interested in it, but that's what I'm with. So if we follow the principles like we did before, we know ideal line sources radiate in what? In a cylindrical form. So if we follow the same principle, surface area of a cylinder is 2 pi RH, where R is the distance from the line source, which meters. What are we eliminating? The constants. We're only interested in how sound is changing. So 2 is a constant, R is a constant, it's gone. Line H is a constant, it's a defined line. So area is equal to what? The R. So if you double your distance, you're basically doubling the surface area. So from there, you can deduce that when you double your area from your distance from the source, the line array, you're only doubling the surface area. You're not quadrupling the surface area like in point source. You're doubling. So what does that mean? So line sources are more focused than your old point sources. Everybody's experience, it gets to your experience. That's what everybody knows. when you're in, so that is why line sources are used mainly for you want to focus your sound to audience. You don't want to spill your sound everywhere. If you're in a reflective area, you want to capture the audience. You don't want the sound to spill these walls and excite the auditorium of the venue. The line source is the way to go. Yeah. Okay. So as far as coverage is concerned, the point sources are better at coverage than line sources, but the line sources have the application for why it's necessary, for a system with a limited surface area coverage. Okay. While point sources have their own applications. It makes sense. When it comes to intensity, we said intensity is what? Power over area. Area is to pi what? RH.
Sorry,
Yes.
sir. Sorry for distracting you for stopping. I don't want to lose my thought. You just said that when it comes to in terms of coverage, point source is better than line source. I hope I got that right.
Not better.
Or more. What would be the word now?
Point sources have wider coverage than line sources.
How is that? Because I know with point source you get maximum of 45-degree horizontal and you have 90 degrees, whereas for line source speakers you have up to 120 degrees, 100 degrees, 110 degrees. So I don't know how you can help me.
Okay.
Just touch on that, please. That will really help because I'm a bit. I wouldn't say confused on that part, but for the betterment of others, and please help us clarify that.
Yes.
Thank you.
Okay, that's fine. Yes, you're welcome. Of course, line sources these days, you can have a line source that is defined by maybe 90 degrees or 80 degrees horizontal a lot of times. Then you have fins or flanges that help you to open it up to where? To 100 degrees, 110 degrees, or 120 degrees, especially used for downfield so they can cover the areas up front much better. You understand? But that is an application situation that allows the line array to do what a point source would do easily, normally. You get what I'm saying? But it's the base cabinets themselves really come with 80 degrees, right? They come 80 degrees, sometimes 90 degrees. But you can have point sources actually to in Nexo. We have some point sources that do 120 degrees horizontal. As in a normal point source cabinet. Okay, what I'm saying. So traditionally, point source will there are point sources that will do 60 by 60, 60 by 90, and other different angle configurations. But for the most part, there are point sources that can do even wider, as in naturally. But a line array will do traditionally 80, 90 degrees normally, and of course for downfields you can do 120 degrees, or maybe 110, sometimes 100, as the case may be. And on top of that, point sources can do what we call variability, in the sense that they can have a different angle at the top of the horn, maybe a narrow angle, and then a wider angle at the bottom of the horn, and then a different vertical angle. You understand? So those different, how do you put it? The different point source configurations that allows it to be very versatile. But of course, like a line array traditionally would do tight angle horizontally. That's one. But when it's the vertical, remember, the line array vertical angles are very tight. So you can have 2 degrees, you can have 0.1 degree. Sometimes the entire line length of a line array can be 50 degrees horizontally for a long line array. Maybe, but you have a short line array, you're having tight angles. So we're looking at the coverage, you're looking about from both the vertical and the horizontal point of view for what you want to do. But traditionally, ordinarily, one point source cabinet, is capable of doing what you might need 6 line array cabinets to do. You know what I mean? So that speaks to the ability of point source to do higher coverage or more coverage than line arrays. I hope that clears what your question.
Yeah.
Hello?
I got what you're saying, sir. Can you hear me?
Okay.
Yeah, I get.
Yes, I heard
I get what you're saying. So in other words, point source in a context is more proficient than line source. Like based on a context or application, based on an application that you're using for, could deliver more in terms of coverage than line source based on a single
Exactly.
analysis.
Exactly. As from that point of view, one cabinet of a point source can do some serious vertical and horizontal angles. One cabinet of a line source will never be able to achieve that. We need several to actually do it.
Because the vertical angle is always small when it comes to the
exactly
to the point line speakers. Okay.
Right.
Yeah, but one more thing, sir. One more question. I hope everybody have their answers. Why? Because there's this general concept of how line speaker waves travels in cylinder. It travels in cyclical shape. Why line speaker travel in a straight format? All right. And it's explained that because point source travel in more like a cylindrical format, the tendency of obstructions is more susceptible to obstruction the line speaker. Is that true or false? Or is that can you enlighten us a bit more on? I'm talking about the SPL now, the SPL time travel. Yeah. So there's a general notion that line speakers travel in a straight format, more defined, more direct then point source, which could be easily obstructed because of its circle, expansion based on the further it travels, the wider the sound spreads. But it's easier to be obstructed, by an object than line speakers.
Okay, yeah. So basically, to start with, the point source travels spherical point source all the time. Line source cylindrically. 2, the obstruction of sound is dependent on the frequency, basically. So high frequencies are easily impeded, even by water molecules in the atmosphere. Low frequencies, less so. Now, lower frequencies, of course, when you encounter an obstacle, if the wavelength of that frequency is larger than that obstacle, it will bend around it and you hear it. Which is why, if you're inside a car, the doors are locked, and you're playing sound at very high levels, and somebody outside will be hearing low frequencies, and not so much in high frequencies, because those low frequencies bend around things and they can get around stuff. So whether it's line array or point source, as long as the frequency being encountered, the obstacle being encountered is bigger than the frequency, it will stop that. But if the wavelength is bigger than the obstacle, it will bend around it, whether it's line source or point source. I don't know if that addresses it. But the thing about line source is that it can throw far when it comes to SPL. And I'm going to address that in a few minutes. For point source, because the fact that it loses a lot of SPL as you go away from it, and the intensity drops as well. What does that mean? The energy of the point source keeps dropping by factor of 4 before you go from it. So it gets weaker and weaker. SPL gets so that's why application-wise you want to use a point source for short to mid, distance. You want to go further, maybe up to 30 meters, 35 meters. You need a day to reinforce the sound buffer. But that distance can easily be borne by a line source, without a problem. Okay. So I hope I addressed. But I think there are some elements of your questions I'm going to address in further slide. Just give me a few seconds. I'll get it. Okay. Hello.
Sir, I got it. Yeah. Okay.
All right, awesome. So in terms of intensity, we said it's what? Power over area, and power is the same. Constant is 2 pi, it's gone, h is gone, they're all constants. So you have what? Intensity is inversely proportional to what? The radius, or which is the distance. So it means that if I double my distance, I'm going to halve intensity. Or the same scenario for point source, if you double distance, what happens to intensity? You reduce it by factor 4. So you can see from here that the intensity is reducing at a less rate than it does with point source. So there's more energy consistency in a line source than you would find in a point source. And if you carry that over into SPL, as you can see from the initial explanation I gave, at A, you have 16 bits of energy. At 2R, you have 2. Remember, you double your distance, you do what? You double the coverage. So you have 2R, you have 2A. Because of the propagation is symmetrical, you have 8 bits of energy in each of the surface area. And so on. Now, if you work out the project equation, which is given by the square root of the impedance and intensity, you arrive at what P is for the measured, which is our starting, which is what P is square root of intensity, which is 4 pascals, and the R, which is a reference, is measured is going to be the square root of 8, which is 2.3. Okay. Now, if you bring in the equation for SPL, so you have to look 10 P2 P1. P2 is what measured. P1 is reference. If you work that out, you get minus 3 dB. When you double the distance from a line source, you are going to double, you half your intensity, and there's going to be a 3 dB change in SPL. So you lose only 3 dB as you go double the distance from a line source. So what that speaks to the consistency of flow, of energy consistency, of SPL consistency, which is why the line arrays are used for what? For long throw application. The acoustics, the maths explain it, and it bears, improve, from these equations. Any question?
Nothing. No one has asked a question.
Okay. Can you ask, as any of your guests encountered of this theory in their experience? Have any of you guys been through this whole line source and point sources behave?
Guys, the question is for you. If you can hear us, can you drop your response? Has any of you had this? What's your experience with what you just said? Mr. John, can you rephrase the question?
Yes, have you had experience, been through this theoretical explanation of the behavior of points and line source in your experience up to this point, or some form of theory that covers this, what I've just been through? So just let me know in the comment section, and you'll get to know. Okay, so point source versus line source. I don't want to cover that. I already did that before in the first. I was talking about point source, so we can skip that now. Line radiation. Okay, so wave propagation. Air molecules bounce into each other, creating what? A change in air pressure. A change in air pressure. Now, when the air pressure is high, which is compression, the sine wave is at what they call a crest. It's peak. When the pressure is low, it's at the rarefaction at the trough. So you can see the speaker here, or the sound source, and then you have the rarefacted particle of, air. And when they're compressed, rarefaction, compression, rarefaction, compression, till it gets to air. Now look at this sinusoidal. So you have the trough, as indicated in the arrow, and the crest, and then you have the trough. So when you see that sine wave, that's not really how sound looks like. So this sine wave is just a representation of the compression and rarefaction of the cresting and the troughing of the particle sound as it travels from the source to your ear. You understand that? Okay. So wave propagation, when I talk about wavelength, so pretty much this is what I mean. So compression when the driver is moving. So if you relate to speakers, compression is when this, when speaker is moving in and out, like vibrating, the speaker expulsion. So when it moves out, it's causing compression. When it goes back in, it causes expansion. So wavelength is the distance over which, yes.
Sorry, can you repeat that question about their experience again? They said, I just got feedback, they said it was a bit distorted from your end. So the audio energy they were getting was distorted. So please, sorry for taking you back, about the experience. Okay. I can hear what you asked about the experiences.
Okay. Yeah, I'm asking if, from what I just explained, let me see if I can make some adjustments. Are they familiar with a lot of what I've explained? Have they come across it previously? Is it new to them? And if they want extra resources, they should share their contact with you, and then I can, if they want more information, I can share with them. For those who want to go even deeper, who have not experienced this before. But as audio engineers, we describe ourselves as engineers, right? We think about connecting systems of gears together. It's always good to know the fundamentals and the granular detail about working with sound, right? So we need to know it down to molecular, particular level, which is what I'm trying to bring to the table. So of course, with this understanding, if you're going to apply design a system with a point source, okay, this is why I need to design this way. This particular situation requires coverage rather than throw. So I shouldn't put the line array there. If you throw, then the line will be more suitable. So all kind of considerations in terms of how you deploy systems goes back to speak to what understanding of the theory of what point source align sources. So if you've not encountered this, you can get, and if you want more information, let us know, and we'll see how we can support you on that. Okay.
Okay, sir, thank you.
I hope it's all right.
Yeah, okay,
so
sorry, the feedback is not that your audio is bad, it's the internet. The internet fluctuating, so the audio seems to drag and gets cracky. But yeah, so I read the questions through the chat, and I'm waiting for feedback from them. Yeah.
Okay.
Yeah,
okay.
But I will appreciate the resources afterwards. I will appreciate the resources afterwards. Yeah.
Okay. Fine. All right. So going further, I have a little bit more, and we should wrap up in a couple of minutes. All right. So I have this wavelength. So wavelength has to do with what, as you can see, indicated in the distance from this peak here, or this crest to this other crest. Corresponding crest is what is a wavelength. So let's say the distance from any point on this sinusoidal wave, the sine wave here, if the distance from this point to this point is a wavelength. So from any point to a corresponding point, on the other is basically a wavelength. All right. As you can see here, you have the point where the lines are so compacted is compression, and where they are spread out is, and so the lines express the particle velocity and motion of the sound wave, and this graph expresses, what's going on. So in a sine wave, where you see, that's compression going on there. If you see the trough, it's a rarefaction that's going on there. Okay, so talking about phase and frequency, you can see 100 hertz. 100 hertz, you can see it's what it is here. 200 hertz is twice the frequency, and you can see basically two sine waves are inside of 100 hertz sine wave, and correspondingly on 400 hertz as well. I will tell you the significance of that in a minute. So phase and frequency, you have phase is the time difference between two sources times 360 times frequency, and to give you that. So I will still piggyback that, but I want to give you the basic foundation of where we're going to. So you can see phase relationships where you have this sine wave in red and this one in green. If you add these two together, it results in a doubling of amplitude. Okay. Now you have, so if I go back a little bit, so you have red and green, gives you orange, right? So you have here green. So the green is superimposed over the red Okay, so basically there's zero phase variance between the two of them. So they double in terms of amplitude. So think about a line cabinet, two boxes against each other with zero phase. So they're going to produce, 6 dB louder sound than when one of them is, radiating. If there's a 20-degree phase variance between two cabinets, 20 degrees, it will give you less than 6 dB. It's not going to be destructive, but you have less than 6 dB. If it is a 60-degree phase variance, you're going to also have less than 6 dB. You're going to have 3 dB boost from the two cabinets. Okay, you're getting gain, a more improved SPL from the cabinets. If it's a 120-degree, two cabinets, 120-degree out of phase, you are having no amplitude boost. You literally will be better off using one cabinet by itself. So the second time is irrelevant. The second cabinet is irrelevant. Okay. If there's a 150-degree phase variance between two cabinets, you're going to be losing. So it's not constructive. You're losing, losing level SPL. You're around 80 degrees phase variance, so you're in cancellation. So the peak and trough in red and the green sine waves neutralizing the relative pressure difference. Okay. Now let's keep that somewhere because I'm going to draw that back in at some point. Now there's some kind of line arrays where straight arrays where it's an array with zero angles between the cabinets. Okay. As you can see, the simulation there, straight arrays, as you can see, very straight. It's great for long throw. If you're not directly on axis, or if you're outside the coverage pattern, your experience will be different. It doesn't have a constant coverage, but it's very good for long throw. And frequency response is dependent on the listener position. Now, how do you know that? This is actually a real simulation here, and this graph shows different listeners. So you can see it's a little bit, the guys where in the blue area are having fun. White guys in orange and cyan here are not enjoying themselves so much. They can hear, but yeah. So for a straight array, what we call the near field and far field. The far field is where the inverse square law applies. So you have doubling of distance, you lose 6 dB. That's the inverse square law. That's the far field. The near field is before the far field, and the sound wave propagates according to the shape. So basically, if the near field and you're doubling your distance, you're losing only 3 dB, which is typical of a line array behavior. Now, line arrays also get to a point where the far field, where it stops behaving, losing 3 dB and starts losing 6 dB. So if the source is in a straight line, sound propagates by cylinder, SPL drops at 3 dB per doubling of distance, limit from near to far field. Okay, so the equation there, RO is equal to FL2 over 2C, will give you the where the far field or near field is for every given frequency. Okay, so at one point I'll share this with you so you can use that for your calculation. So you know when your line array is actually like line array and when it's deviating start giving like a point source pretty much. Now we have constant coverage at 5 degrees. So you have less throw. You can see here that up front here, very, but far not so good. Yeah. So you have less throw due to vertical dispersion. There's constant frequency response over distance, and it is great for areas up front. And so you can see here in the coverage pattern here, it's a little bit more compact. So there's kind of similar listening experience, mostly up front. Constant coverage array at 3 degrees. You can see here it is not great for up close here. So it's missing something missing here, but in the mid areas, middle section, more line array like behavior in the section, but not great for far through applications. So there's also consistent frequency response over distance. As you can see here as well, the coverage pattern is a little bit compacted, so it shows a little bit consistency. Now go to array comparison. You have the long straight array, great for long throw. Constant curved array, what areas up front? Constant curved array, 3 degrees, middle section, and then the all-round base array solution, which is J-shaped array. Now, what does that do? So J-shaped array with progressively curved line source will be great. So you can see constant level can be achieved across the array. So you can see far throw is fantastic. Mid, it's very good. Up close, not so much, but if you want to cover the front area, you just increase the J angles and you will cover the upfront areas. And you can see that the curvature of the line will vary. The consistency of the frequency response along the audience area. For J-shaped arrays, tonal balance stays consistent. Everyone gets the same show pretty much. And then you can see here how compacted. Everyone literally gets the same show, in terms of the coverage pattern here. I'll skip this. Well, maybe if you want to keep that as a rule of thumb, we want to determine what is the line of the source array length for any given venue. In next we use venue depth divided by 16, and we give you the number of cabinets approximately. If you want the position to do a simulation straight away, just a rule of thumb, then of course you need to do your simulation to be able to get a proper scientific evaluation of the requirements for the venue. All right. So line source criteria, spherical sources. So you can see here, this is more, let's say 1, 2, 3, 4 cabinets of a line array put together. So LF source criteria. LF source criteria is I spoke about it before, but now I want to go a little bit deeper in it. So the distance of source elements. So you can see the distance between the center of this cabinet and the center of this cabinet, this D. So you can see here D is greater than the wavelength of the frequency in question divided by 2, and you have low frequency lobing, and D is less than the frequency of the wavelength of the frequency in question. You have summation. Now this is very, very important, gentlemen and ladies. This is very, very critical. So a line array, for summation to occur at the low frequency, the distance from the center of one cabinet to the next cabinet, maybe let's say that cabinet is going to be doing down to 85 hertz. Okay, that distance, if you calculate the wavelength of 85 hertz, okay, that distance needs to be less. The distance between those two cabinets must be less than that figure. So let's say 85 hertz is 4 meters, right? Divided by 2, that is 2. So the distance between those two cabinets needs to be less than 2. As long as it's less than 2, there's going to be summation between those two cabinets, because that's what we want for a line array. Summation down to its cross point into the subwoofers, and also summation down to the cross point going into the HF. So this criteria must be met for summation to occur. Now, for what about high frequencies? Because now, of course, it may be easy to achieve low frequency summation because of the cabinet size itself. But we're looking at high frequencies where it is impossible to have cabinets close enough to physically impossible to bring them close enough because of the very high frequency and the very small wavelength. So different criteria is used in this case. So at high frequencies, you can see here that the delta X, yeah, it needs to be the delta X needs to be greater than the wavelength, the quarter wavelength at that high frequency in question, and delta X, which is here, it needs to be lesser than, the wavelength of the high frequency in question. So in this case, you have high frequency lobing, and in this case, you have more pattern control in the high frequencies. Now you see here what we're trying to. A lot of manufacturers, that's what we try to achieve, so that the wavefront in front of the high frequency is as flat as possible. It needs to be as flat as possible. If you can achieve flat, some manufacturers go for flat, some go for slightly curved, but you don't want it to be curved, like a sphere. That's what you're trying to avoid. So the technology that go into designing of a waveguide is to get the HF to radiate at a flat or slightly curved wavefront to achieve summation. Let me give an example. So you can see here 2 cabinets with the HF together. So you can see here, and you can see the curvature, and the sound is coming from the compression driver. Curvature here. The same thing for the one below. Now, if they radiate in this way, you have this curvature creating comb filtering. Yeah. Now, this is what happens when you put 2 point sources together. 2 point sources without a waveguide, with a regular normal horn. So there will be HF comb filtering, which is why it's never recommended to do that. I've seen some places in Nigeria where some churches, they put 2 point sources together and they weld it together to try to create a line array of some sort. Never a good idea. Summation will occur at the low frequency, no problem. But the HF, not so much. Okay. So you can see here, in order to deal with this problem, we want to minimize delta X. So this needs to be smaller. Okay. So reduce the curvature or achieve flatness. That's what we want to achieve. How do we do that? So you can see energy from the center, which is this, and there's energy also arriving from the flare, the side. So the goal is to increase the path length of the energy from the center. You understand? We have to increase because it is traveling the shortest distance, which is what is causing the the spherical nature of the HF. So you can see here, we increase this path length to allow it to arrive just about the same time like energy coming from the longer flares here. So this energy from the center arriving with energy from the flare, the goal is to increase the path length of the energy from the center, and the waveguide is used to flatten out the wavefront. This is why line arrays have waveguide for that exact purpose. So different manufacturers have different ways of achieving that. In Nexo, we have what we call the hyperbolic reflector waveguide that does the goal of, increasing the path length of energy from the center to create that flat wavefront in front of the HF for coherence. Okay, so a typical example would be flat wavefront versus slightly curved. So now it's about what sometimes what sounds best. Some manufacturers will say, okay, we want a perfectly flat wavefront, zero split angles between the boxes. So you can have this result in a very strong vertical pattern control. Zero split angles between boxes, slightly curved wavefront. So in this case, you see slightly curved. You have tight vertical pattern with some lobing. So that's good. This is kind of perfect. This is okay. But sometimes the what they call it, the harmonics that maybe sound good to some people with that. So you have flat wavefront versus slightly curved. So now we have a perfectly flat wavefront, and then we have curvature. Initially there was no curvature. Now we have a curvature to the boxes. Side beam of energy, not necessarily connected to the arrays. Now we have a slightly curved wavefront, add a slight curvature to the array, and the boxes interact in a more cohesive fashion and consistent dispersion of the entire array. So depending on the technology preference of different manufacturers. So of course the goal is to minimize that distance. So slightly curved, we can argue all day long which one is best, but at the end of the day, the results depend on the preferences of the different manufacturers. But you defeat the whole issue of creating what they call it comb filtering when you don't have a waveguide in the system. Yes. So that's I'm going to round up with this. And if you have any questions, you can relay them right now, or you can drop questions, and let's see if we can deal with them within the next couple of minutes before we run up. Hello, Steve, are you there?
Yes, I'm here. That was fantastic. So yeah, I have a question. So what you're saying is, whenever there's a point source speaker, all right? Can you hear me, please?
Yes, I can hear you.
Okay, whenever there's a point source speaker that has been converted to in a line array format, will I be accurate to say that there's a cancellation in the high frequency area when they are brought together, arranged like a line speaker, because they don't have a waveguide?
Correct.
Okay.
Absolutely.
So
yeah, we'll definitely
so that means most, I may not say 80%, but most of the speakers that are sold in Alaba that claim to be, or that sold in Nigeria that claim to be line arrays, local speakers made and all that, they are not going to give us, obviously, the kind of energy or clarity or full capacity or potential of the speakers that a real line array or pointer should carry, right?
Absolutely. The technology that goes into creating a line array, especially when the waveguide is quite huge, and to make sure that it is as the summation is perfect. That is why you see premium arrays are so clear at the top end. It's because they're taking all this into consideration to make sure that you have the best sound. That's what we also have in the Nexo. I don't know if you can see behind me. Can you see behind me?
Yeah, we can. I was about
yeah,
talking,
so this is...
Yes, we can. I was about talking about that because you could just take us. Yeah. We need to know about, guys, we need to know about Nexo YAMAHA systems. It's coming to Nigeria. This man is helping us to bring it, and we must buy it for our churches, for our clubs, and all that. So probably you would explain that. Maybe you just take us on a short term, about. You didn't even talk about the Rivage, because that's anyone in the room. That's the crazy system.
You can see the Rivage behind me as well. Yes. There's a lot to cover, and I hope that there will be another opportunity so we can actually, talk about the meeting consoles and stuff. We'll get there. But of course, what I see there is the STM system. It's a modular system. This is a ground stack version. And the bottom, the subwoofer, the S118, is one of the most powerful subwoofers around. It does 143 dB, single 18-inch, high excursion, bandpass subwoofer. It is very powerful. most double 18-inch subwoofers will only equate to it because just check around. It's one of the most powerful double 18-inch subwoofers do down to 30 or 25 hertz at 143 dB. This guy, that's one that does down to 25 hertz and 143 dB for a single 18-inch. So it has the low end and SPL. And then the nozzle is at the top, you have the nozzle, which is what we call this nozzle here. Is designed like a jet engine nozzle, pretty much. Yeah. So and it's basically laminar flow. There is so perfect. So that there's zero turbulence. So you need to hear it to believe what I'm saying. The technology is tight. And it does basically from 25 hertz up to maybe 120 hertz, depending on how you want to use it. The one in the middle here, called the B1 is the base unit, taking it from say 60 hertz to 120 hertz, and very powerful as well. And then you have the top here, which is the M28s. The M28s will do from say 85 hertz to 20k. Through 20k, you understand? And very, very powerful. It comes in 90 degrees. And then, of course, you have a wider horizontal for 120 degrees. And then also, we have another module, which is called the main module, which is not here at the moment. But this system, as it is, can scale up to, you need to see that because I have a full presentation for that, so let's keep that. But it can scale up to a system-wide 4-column systems, you understand? That no other system can match. SPL is very powerful, modular, defined, and very powerful. Hopefully, we'll come to Nigeria, we'll come with this system so that you guys can come in and actually listen and hear how it sounds. It sounds beyond amazing. Before I please, I'm going to bring in this thing because this is important, especially for my brothers in Nigeria.
Yeah, sorry, can you hear me? Sir?
Yes. Can you hear this? Can you see my?
Hello?
Can you see this? Yes.
Yeah, someone dropped a message. One of the guys, he says that he has experienced the power drop in relation to distance using a point source speaker. So that was when you were talking. He said he's noticed a power drop in his name is Abisola Ogenigwe. He says that he has experienced the power drop in relation to distance using a point source speaker. So that's the
fantastic.
Yeah.
So theory and practice actually do coincide. So not every time, but for the most part, which is why it's good to know the theory and to know how to expect, when you're putting systems together. Now I want to show you guys this, which is very important. I just remember now. Remember, I said something about pattern control. Yeah, pattern control. Now, basically, what do you call it? So you have wavelength, right? It's what? What is formula for wavelength? Somebody help me. Formula for wavelength. I need somebody to put it in the chat right now. Steve, can you prompt the people to what is formula for wavelength?
They are hearing you, but I don't know. I don't know.
Speed of sound divided by frequency. Okay. So, what is the wavelength of 85 hertz? So, speed of sound is 343 divided by frequency is what? 85 hertz. If I work this out, this will give me about 4 meters. 4 meters, right? Now, if I have a line array, this line array will control the sound down to 85 hertz perfectly well. So you don't have looping, you don't have sound in the vertical, it's playing, the cabinet will contain the sound and will direct the sound down to 85 hertz. That's what I mean by pattern control. So that your subwoofers can be doing the job from 25 hertz or 32 to 85. Lovely. While this guy will be, so there's no overlapping or to a less extent. So this is a very controlled, a very directed sound. So this is pattern control. If this array is about maybe 3 meters long, let's say, what it can control down to what? So lambda is C over F. So 3 is equal to 343 divided by F. We don't know what F is. 3F is equal to 343. F is equal to 343 divided by 3, which is 114 hertz. So a 3 meter array will control down to this 114 hertz very, very quickly, while the remaining lower than that will diffract around it pretty much. Now, when I do this, I've been to some churches where they put a line array with 4 boxes. Yeah, each one box is maybe 3.5 meters in terms of the height. So 3.5 times 4 is 3 times 12. So basically it's 1.4 meters. 1.4 meters. Now, 1.4 meters will be what we control. It's going to be 343 divided by what? By 1.4. Can somebody help me with that number? 343 divided by 1.4. So it's going to control around maybe 300, somewhere around that, I think. Okay, so frequencies
that's
from
245. 245.
245. Okay, good. So 245. So it can only control down to 245. Everything else happening under 245 is a point source. It's a point source. You might as well just put a point source there. Do you get what I'm saying? So this is not really a line array. It's a line array only from 245 hertz up. Down, it's not. To properly enjoy the benefit of a line array, you need this length. You need pattern control. Do you get what I'm saying?
Yes, sir.
Yes. Of course, I mean, there could be other reasons why, but I know sometimes everybody wants to get a line array. So if you want throw, yes. If you don't have, if your church is less than maybe 35 meters, you don't need a line array as such. If you want to spend money on it, that's fine. But you can put a point source. And there's some, sometimes, okay, line arrays, a lot of times is 130 dB, 125 dB, or 136 dB. Sometimes that's a very high. But now there are point sources that can do 141 dB. That some line arrays can't even achieve. We have that in our Plus series. Our Plus series can do the P15 or P18 can do 142 point source. So if you have that as your left and right in that kind of setting, and then a delay, you can really cover 35 that's at the low cost and price point. You understand? And putting 4 cabinets, which is in question mark a line array, but not really line array, because it's not really fulfilling the behavior, because below certain points is behaving like a point source, which is actually what some sources do as well. So if a point source is maybe, if this card box here, and then this is the, if this is maybe 700 mm per 7 meters, so it's going to do as much. It's going to behave as a point source down to the geometric, the dimension of the cabinet, while everything else, which is what is expected of a point source. So a point source will not do pattern control, but a cabinet of limited cabinet, a line source of limited cabinets will also literally behave like a point source. So there's no real need to deploy expenses just because you want to have a line source. But theoretically and practically, not so much. I don't know if you have any questions. So there's still more to say, but I have an opportunity to actually go in more deeper. But I think we spend a lot of time. So I would like to rest my case here. If there's any questions, go for it.
Can you give us additional 20 minutes?
20 minutes. Let's 5 minutes.
At least to talk to us about, bring this in, maybe just give us an overview about that thing behind you there, the Revage. Or just complete on this, what you're saying on this marker board, and then just give us a summary of what the Revage can do. So there are people here who wants to get a console for their churches, and then how linking up with you guys, how can they get it through you and all that. And for those that have YAMAHA consoles, who have some challenges in terms of repairs, what can work, probably you just give us. So guys, if you have any question, you have the TF series or the CL, or and you just need to drop your questions so that he can attend to them.
I'll try limited time. Of course, that's the Revage. That's the CSR3, the control surface, and CSR3 control surface, the DSP RxAX, and then this is the RPI 622. This is Rio. Everybody knows 3224D2. Now this Revage system ecosystem works on 2 networks. We are Twin Lane. Twin is the YAMAHA proprietary network. It's a 32-bit network, between 992 dB dynamic range, which is, I mean, is best out there. It supports up to 400 channels in and out. Latency is very, very low in milliseconds. 12 samples, 13 samples, depending on the frequency, the sampling rate, up to 96K. Each of the Revage system can do 288 inputs if you're using the DSP RxAX, and 120 if you're using the base model, which is the DSP, the RX. There are 3 DSPs, RxAX, which is the biggest RX, and then the DSP, the PM, DSP, what? The DSP. Okay, so so this system can work with Dante, of course, with which Dante based rack, and they can work with the RPIO. The RPIO houses what we call our analog input card, which carries Silk. Silk is a very prized feature in Revage PM. Silk comes from a Red Nibs analog Silk processing, which is a very, very expensive analog gear. and then we'll work with Properties to transcribe it into the digital emulation exactly that is hosted there. And we're the only ones that have the rights to that, you know. And so what it does is add certain harmonics to your to the input channel